Hey there, Adrian Rosebrock here from PyImageSearch.com, and today we're starting a brand new four-part series on deep learning-based object detection. Now, this series is meant to be an introduction to deep learning-based object detection. We're going to start with learning how to turn any classifier into an object detector using traditional image processing and computer vision techniques like sliding windows and image pyramids. From there, we're going to start to get into selective search. Now, selective search isn't an object detection algorithm per se, because in object detection, you're looking to get two values. The first is where an object in an image is located, and this where we consider the XY coordinates. It's the bounding box of where an object is. Secondly, we want to know the label of that bounding box. So if we're running a deep learning based object detector on this video stream, you would expect to see a label for my head, maybe one for my water bottle or my phone or any other objects that are in the scene. Selective search doesn't really know what is in an image. It's just saying, hey, this region over here, it looks like it could contain an object. So spend a little bit of computational resources trying to figure out what that object is, and maybe ignore this region over here because it doesn't look that interesting. So using selective search, we'll then go into part 3 of this series. And part 3 says, let's replace a sliding window and image pyramid with selective search. Let's see if we can get our pipeline to run faster. Let's see if we can get more accuracy out of it. And then the final step is we're going to build an RCNN-like deep learning object detection pipeline. And that's going to combine all of the steps we've learned thus far. You're going to learn how to use selective search to propose regions to our CNN where objects could be. We're then going to take these regions, we're going to make sure they're labeled, and we're going to train a CNN on these regions. And then finally, for inference, we're going to use selective search again, but we're going to take those ROIs, pass them into our CNN, and then we're going to get our final object detections. And essentially, that is what the original RCNN architecture is. So by the end of this series of tutorials, you'll not only appreciate how deep learning object detection is done, but you also have a working RCNN pipeline that you can use for your own projects. But why go through all the trouble of studying this topic in depth? Why not just jump immediately to your YOLO detectors, to your SSDs, to your faster RCNNs, to RetinaNet, to other models? Why go through this detailed study? It's a good question. And I think there are two things you need to consider here. If you're serious about studying deep learning and computer vision, you need to understand where these models come from, how they were built, and the steps that are taken to create them. And of course, we're going to implement all of these by hand as well. So you're going to get a really, really deep understanding. And secondly, and this is something I've reiterated throughout the entire course, is you've got to bring the right tool to the job. Learning computer vision, learning deep learning is about filling your toolbox with a varied set of tools. So when you encounter a problem, you know which tool to use. Altogether, that means you need to have an appreciation and understanding for where these algorithms came from. Because some of those algorithms that aren't as sleek or as sexy or as cool, they're still highly applicable. You just got to know when to use them. So we're going to study all of that in depth in this series of tutorials. But today, in part 1, and I have the text version of the blog post pulled up, we're going to focus on how we're going to turn any pre-trained convolutional neural network into an object detector. And we're going to be using a traditional computer vision approach using sliding windows and image pyramids. And here you can see all 4 parts of the series have been laid out. So let's start with discussing what the difference is between image classification and object detection. So in traditional image classification, we present an image to our convolutional neural network and we say, hey, give me one label, just one label that characterizes the entire contents of this image. So back during the ImageNet competition, classification was one of the most challenging aspects of the competition. And we really struggled to get high accuracy until we started training convolutional neural networks. And then with the creation of AlexNet, we saw this massive jump in accuracy. So that was 2012, 2013. Obviously, we've progressed a lot since then, but the simple concept of image classification hasn't changed. You take one image, input it to a model, you get one class label out that characterizes the contents of that image. And that's exactly what we've done here. We have this input image of a beagle, which is a type of dog, and we ask our convolutional neural network, classify this image and tell me what is in it. So that's what we get here. We get beagle as the output class label. You can thus think of image classification as one image in and one class label out. Object detection, on the other hand, is more advanced. It's going to give us two values. We're going to get the bounding box location of every object in the image. So here are the two bounding boxes. And then along with that, you get the class label for each bounding box. So with object detection, you're going to still input one image, but you're going to obtain multiple outputs that include the bounding boxes and the class labels as output. So that kind of raises the question then, if a model is trained for classification, which by definition just gives us the class label, how can we take that model and turn it into something that gives us the output over here? The answer is that we're going to use algorithms that were used in traditional image processing pipelines, such as Haar cascades and Hog and linear SVM. And particularly, we're going to use image pyramids, which I've discussed previously, as well as sliding windows. So if you haven't seen these tutorials before, I would strongly recommend you go back and read my sliding window guides. We've covered them previously in this course. If you need just a gentle refresher, go back, skim these two tutorials. They'll give you a really good understanding of how sliding windows work and how they enable you to locate objects in an image, as well as image pyramids that allow you to locate objects at different scales. Really, really important reading if you haven't seen these tutorials. So definitely press pause, go skim them real quick, and come back if you haven't seen them before. So continuing on, let's just start with a really high level overview of what both an image pyramid and a sliding window do. So here is an example of an image pyramid. At the bottom, you have your original input image, and then each subsequent layer in the image reduces the size of the image by a factor of 2. So we're cutting the size of the image in half at each layer of the image pyramid. So here we take this input image, we divide it by 2, and this gives us half the size of this one. Now, what's nice here is that objects that looked really, really big here in this original representation of the image now look smaller over here. That's really important when we start working with sliding windows. And we can continue to do the same thing for each layer of our image pyramid. So once we've constructed all the layers of the pyramid, what we're now going to do is apply this technique called a sliding window. A sliding window has a fixed width and a height, and as this image shows you, this fixed width and height rectangle is sliding left to right and top to bottom. And at each stage, at each stop of the sliding window, it's going to extract that ROI and pass it into a model for classification. So what you end up doing with image pyramids and sliding windows is you create this algorithm that starts with the original input image. It's going to run the sliding window across it. And then we're going to go up the next layer. The image is reduced in size by half. Slide the window across it. All right, have the image again, next layer. And what you end up doing, and as this representation shows, this bounding box is going to allow you to classify objects in an image at different locations and, most importantly, different scales. So if you had multiple objects in an image and one is in the foreground and one is in the background, the person closest to the camera is going to appear larger. And that person in the back, if you have a fixed size sliding window, it might not be able to detect them. But if you're able to reduce and manipulate the size of the image pyramid, or start with a higher size image pyramid and then progressively downsample the image, you're able to adjust the scale of the objects in the image, thus giving this fixed size sliding window a better chance at locating each of the objects. Now, the final step here, and this is something you've seen before with object detection, is when our sliding window gets close to an object, it starts to get excited. It's going to start returning higher probabilities of a positive detection. It's a good thing. It's indicating that our model's firing and giving us positive predictions the closer and closer it gets to an object. The downside then is that we have these multiple overlapping bounding boxes, even though there's only one object in this image. So what do we do then? How do we collapse these multiple overlapping bounding boxes into a single representation? That algorithm, which we've also covered, is non-maxima suppression. And what this does is it takes the original bounding box locations as well as the probabilities of these bounding boxes, and then it looks at them and says, okay, how much do you overlap with this one? And how much does that bounding box overlap with that one? And oh, what's your probability? So what it's doing is it's suppressing weak overlapping bounding boxes such that you collapse all of them down into a single bounding box. And if you have multiple bounding boxes in an image of separate objects, that's okay, provided there's not significant overlap between the two. Keep in mind that non-maxima suppression is only going to examine bounding boxes that overlap. And then it's going to consider to say, hey, do they sufficiently overlap? And secondly, is the probability sufficiently high enough that I should collapse these down? The bounding boxes don't overlap, you don't have anything to worry about with non-maxima suppression. So I've covered that algorithm before on PyImageSearch. You've seen tutorials that have used it already. If you haven't, go back and read my guide on non-maxima suppression. This is an intro tutorial, really, really good one for you to help understand the impact that sliding windows have and how you can reduce those overlapping bounding boxes. So here are the steps required. I'm going to open this up in a new tab. Basically, it's a 5-step process, and step 3 has multiple steps, sub-steps applied within it. So we're going to start with our input image. We're going to build our image pyramid so that we have a multi-scale representation of the image. And then we're going to run a sliding window on each layer of the image pyramid. And for each layer of the image pyramid, we're going to and for each sliding window location, we're going to pull out that ROI. And we're going to say, hey, extract it, pass it through the CNN, classify that ROI. And you want to say, is this probability sufficiently large? Or am I just getting like background noise, background classification that just should be wholeheartedly ignored? So what you do then is a simple if statement. You say, if the probability of this positive classification is greater than whatever my threshold is, I want to record the location of where this classification took place. So you do that for each layer of your image pyramid, and then you do that for each step of your sliding window. The output of all of that, you're going to want to apply class-wise non-maxima suppression. Why class-wise, and what does that actually mean? Well, consider the ImageNet dataset. There's 1,000 class labels that model can recognize. And let's say we're classifying like a doggy daycare company, and they need to keep track of the dogs, and they want to classify the species of each dog as they're running around the playpens. So by definition, each of those dog species is a different class, and ImageNet recognizes each of those classes. So if you have a bunch of beagles, mingling over here, and then a bunch of, Dobermans over here, and then maybe some labs, up in here, what you want to do is apply class-wise non-maxima suppression, because you don't really care about applying non-maxima suppression if the class labels are different. Because if the model was reporting a different class label, then they're not the same object. They could be overlapping objects. They could be two totally different objects. You don't want to accidentally suppress objects of different class labels. Instead, what you want to do is only apply non-maxima suppression to each individual set of labels. So you're going to independently apply non-maxima suppression to the Beagle class, and then independently a whole nother round of non-maxima suppression to the Labrador class, and then to the Doberman class or whatever other species of dog I'd used in that example. So once you've done all that, you're going to return the results to the user. I want to show you the output before we get too far. So here is an example of applying this object detection algorithm to an input image of a stingray. So we're going to construct our image pyramid, and then we're going to slide our window left to right, top to bottom. And we're going to get these multiple locations for each of the bounding boxes. We're going to apply non-maxima suppression. It's going to suppress these weak overlapping bounding boxes and give us this final output image. We could do the same thing here as well. This one is of a hummingbird. So as you can see, we're getting really, really high probability predictions at each step of the sliding window surrounding this hummingbird. We then take the probabilities, and then we're going to apply non-maximum suppression to give us the final correct object detection. And again, keep in mind, the model we're using is strictly classification. This model only cares about predicting class labels. It has no concept of predicting the bounding box locations of an object. But by using image pyramids and sliding windows, we can almost trick the model into doing it. Now, of course, you'll learn how to train models that naturally predict XY coordinates of bounding boxes and labels. In fact, that'll be one of the next object detection courses you want to take inside PyImageSearch University. But we have to appreciate and understand the history of object detection algorithms, how we go from sliding windows and image pyramids to region proposal algorithms like selective search, and then finally embedding the entire bounding box prediction process into the network itself. So you can kind of see where we're going, but let's take a look at our project directory structure. We have a single driver class here, detect with classifier.py. It's going to perform object detection using a pre-trained convolutional neural network. Inside the PyImageSearch module, we have this detection helpers.py script as a few convenience helper functions that we're going to implement. And then finally, in this images directory, we have 3 example images of a hummingbird, a lawnmower, and a stingray. We're going to learn how to apply object detection to each of these images. And finally, when we're at the end of this tutorial, we'll kind of look at some of the limitations of this approach, some of the drawbacks, and what we can do to improve upon our method. I'm going to open up PyCharm here, where I have the entire project directory structure pulled up. And let's look at detection helpers.py. We have 2 functions here, sliding window and image pyramid. Let's start off with the sliding window method. So again, this is a function that's going to slide a fixed size bounding box from left to right and top to bottom across an input image. And at each stop of the sliding window, we're going to pull out that region of interest and pass it on to our calling function. So this sliding window function accepts the input image that we're going to apply the sliding window to. We have a step size. So we could take one pixel step to the left, 1 pixel step to the left again, and then we reach the end of the image, then we go down 1 pixel. You could do that. The problem there is that it's computationally inefficient to take only a 1 pixel step at each step of the sliding window. It's going to take too long to loop over that entire image. So what you do is specify a step size. So instead of just shifting 1 pixel at a time, you may shift 5 pixels at a time, 10 pixels at a time, 20 pixels at a time. This is a parameter you're going to want to tune to balance speed and accuracy. Typically, you'll see the step size between 5 and 20 pixels. And right here, you can see we have a window step of about 16 pixels here. So value you might want to tune. Then we have this window size. This is the width and the height of the bounding box or the region of interest that we're going to extract at every step of the sliding window. So let's see these parameters in action. First, we're going to loop over the y-axis. So we're going to start from 0 and go to the height of the image minus the height of the window size. And we're going to do that all in step size increments. We'll do the same thing for the x-axis here, looping over the width of the image, and then we're going to yield a 4 tuple of values to the calling function. So this is the starting x coordinate of the region of interest, the starting y coordinate of the region of interest, and then here is, it's actually a 3 tuple. So this is going to be the actual ROI itself. Here we use NumPy array slicing to extract the y region and then the x region. If you're new to NumPy array slicing, go back to the OpenCV 101 basics lessons of this course. I discuss image cropping in detail, and because you may be confused, like, hey, why are we supplying the y value first and then the x? Shouldn't it be the inverse? No, actually, and that's discussed in the cropping lessons. So go back and watch that tutorial if this seems a little funky to you. So let's move on to the image pyramid. So the sliding window goes left to right, top to bottom. The image pyramid creates a multi-scale representation of the image, starting with the original input image and then reducing the size at each layer of the image pyramid by a fixed factor or scale. So this method accepts 3 parameters. This is the input image that we're going to construct the pyramid for. This is the scale. This is the factor by which we reduce the size of the image in every subsequent layer of the pyramid. And I discussed this scale value in detail here. And you can see Our scale factor controls how much the image is resized each layer. Smaller scale values are going to yield more layers in the pyramid, and larger scales will yield fewer layers. This is another parameter that you're going to want to have to play with, because if you set your scale value too small and you end up with more layers, well, that's just more data that has to be processed. That means your algorithm is going to run slower. But if you choose a large value and you yield fewer layers, sure, your processing pipeline is going to be faster, but with the caveat that some objects may not be detected because you didn't compute enough layers of the pyramid. So then you have this min size value. This is the minimum size that your pyramid layer has to be. And if it falls below this size, then it's essentially unusable to your pipeline. So what we'll do here is just use this if statement, say, if our image size is less than our min size requirements, then we'll just break from the loop and be done constructing the image pyramid. So inside the body of the function, we're going to yield the original image to the calling function. That's the base, that's the bottom layer of the image pyramid. And then we're going to loop over every layer of the image pyramid that we can generate. So we'll first compute the dimensions of the next image or the next layer in the pyramid. That's what this line of code here is doing. We're taking the width, dividing it by the scale, and that gives us our new width. And then using the imutils.resize function, we'll resize the input image to this scale factor. We use the imutils.resize function here because we want to maintain the aspect ratio of the image. If we use the cv2.resize function, then we'd have to manually compute the aspect ratio. Requires a bit more code, so we'll just use the imutils.resize function. I already explained this little if statement here. We're just checking to see if our resized image falls below the min size, and if it does, then we'll just break from the loop. Otherwise, we're going to yield the current layer of the image pyramid to the calling function. So we've implemented sliding window and image pyramid. So let's move on to the detect with classifier function. So this is where all the heavy lifting is done. These are just little helper functions. This is where the hard stuff is. So let's start with our imports. Notice we're importing the ResNet50 function. This is the ResNet50 model. It has been pre-trained on the ImageNet dataset. So this is an image classifier. It is not an object detection algorithm. But using the sliding window and image pyramid approach, we actually can turn it into an object detector. This is the pre-process input function associated with ResNet50. So this is going to do pre-processing and scaling to the input image. We'll also have our image to array function for additional pre-processing, and then our ImageNet utils function that'll decode the predictions that come out of ResNet. We have non-maxima suppression, which I've discussed is going to suppress weak overlapping bounding boxes from the object detection phase. And then here are our sliding window and image pyramid helper utilities. NumPy will be used for some basic numerical processing, argparse for command line arguments. We use imutils for resizing our input image and maintaining aspect ratio. We'll use the time function here so we can measure how various steps of this, or how long various steps of our processing pipeline is taken. That way we can see what needs to be tuned and what can be improved upon. And we have CV2, which is our open CV bindings. Let's move on to our command line arguments. We have a single switch here, image, which is the path to an input image on disk that we want to apply object detection to. So presumably that's going to be one of these three images in our images directory. You can, of course, supply your own images as well. The size parameter is the size of the ROI in pixels that we want to extract at each step of the sliding window. By default, we'll say it's a width of 200 pixels and a height of 150 pixels. However, this is a value you want to tune. One of the problems that we'll see with the approach of using sliding windows and image pyramids, and this is irregardless of whether or not you're using deep learning based models or if you're using hard cascades or hog and linear SVM, is by nature you have to hard code the size of your sliding window. So that means if your objects have different viewpoints or they're captured differently, they're going to have different sizes. So this is a fundamental limitation of a sliding window and image pyramid approach, is that you need to hard code this value. That could be problematic. And it'll potentially lead to false positive detections or just completely nonsense detections. And you'll get to experience that as we go through this tutorial. We then have this min confidence parameter. This is set to 90% by default, and it's used to filter out weak detections. So we extract an ROI and then classify it, and then one of the class labels comes back and says, "Hey, I'm over 90%." We're like, "Okay, good. Let's consider that as a positive classification." If it's below 90%, we'll be like, "No, let's throw that out as a weak detection, most likely a false positive." And this visualized flag here, this is just good for extra debugging purposes for you to see what the sliding window is actually doing. We then have a number of important variables here. This is the width. This is the original input width to the original image width. And I'm going to pull up these descriptions here just so you can follow along with me. So these is a constant that we use to resize our input image to this predefined width. We'd like to have this predefined width or height or whichever dimension you want to use because you want to have a starting point from where to apply your image pyramid and your sliding window. We then have our pyramid scale factor. This again controls the number of layers that are generated by your image pyramid. You want to tune this value based on how you can balance speed versus accuracy. If you're generating too many layers from the image pyramid, your pipeline is going to run way, way too slow. If you're not generating enough layers of your image pyramid, then you're going to miss out on detections. We then have our sliding window step. So at each step, we're going to skip 16 pixels to the left. And once we hit the far right of the image, then we'll shift down 16 pixels and continue that sliding approach. Typical values for your sliding windows are typically 5 to 20 pixels. But if you need large input images, you may want to consider increasing this window step because again, that's where your balance of speed is going to come from. If you have too many stops along the way in that sliding window, it's going to slow down your pipeline. Here we have the ROI size, which is just the size command line argument. And then this is our input image size to the ResNet 50 model. So when we use ResNet, each input image or ROI has to be 224 by 224 pixels. So that's why we define that and hard code it here. Let's continue on. Here we're loading the ResNet 50 model from disk with weights pre-trained on the ImageNet dataset. So at each step of the sliding window, we're going to extract that ROI and then pass it through ResNet for classification. Let's then load our original input image from disk, resize it to this predefined width up here, and then grab the original spatial dimensions from the resized image. Here we initialize our image pyramid using the pyramid scale and the min size, which is our ROI size, which we have right up here from the command line argument. And then we're going to initialize two lists. This is the ROIs list. It stores the regions of interest that were generated from the combination of the image pyramid and sliding windows. So for each of these ROIs, we also want to store where in the image these ROIs were located. So when we classify each of these ROIs and we find a positive prediction or a classification greater than 90%, we can go back to the locations list and say, hey, where in that image, where in this series of sliding windows and image pyramids did this positive prediction occur? And once we found that then we can go back and apply non-maxima suppression to those regions and figure out where the actual object is in the input image. So let's see how long this process of generating the image pyramid layers and sliding windows takes. So we're going to loop over every layer in the image pyramid, and we're going to determine a scale factor, and that's the scale between the original image dimensions and the current layer of the image pyramid. We'll need this scale factor because we want to compute the bounding box coordinates of every sliding window location for every image pyramid level with respect to the original input image size. We have to do that in order to apply non-maxima suppression. If we store just the raw XY coordinates, well then by definition, when the smaller and smaller an image gets, then the more compact the coordinates are going to be, and they're not going to be in terms of the original input image size. So that's why we're maintaining this scale. So for this current layer of the image pyramid, we're going to run a sliding window across it. And we're going to pass in the current image pyramid level, our window step, and our ROI size. And that's going to give us three values out of it. The starting X coordinate of where that ROI came from, the starting Y coordinate of where that ROI came from, and then the ROI itself. So here's the scaling that I was telling you about. Remember we computed the scale right here? Well, now we're going to scale the XY coordinates of this ROI with respect to the original image dimensions. So we take the X coordinate, multiply it by the scale, the Y coordinate, multiply it by the scale, and the width and height are the ROI size, which we got from here, multiplied by the scale as well. So let's take the original ROI and we're going to resize it to our fixed input size for ResNet. That's 224 by 224 pixels. We're going to convert it to an array and then preprocess it using ResNet's preprocessing function. At this point, we can update our ROIs list with a preprocessed ROI, as well as update our locations list with the bounding box coordinates. As you can see, it's a 4-tuple of the X, the Y coordinate, the ending X coordinate, and the ending Y coordinate. If we passed in this visualize flag here, then we'll draw the bounding box coordinates on this original image so we can visualize the size of the bounding box as it slides across each layer of the image pyramid. Finally, we'll stop the timer and measure how long it took to construct the image pyramid and sliding window. So I'm going to actually run this script now so you can appreciate what this script is doing. And I want to specify the visualize flag. Wait for the model to load, then we'll start this sliding process. This green rectangle here is the location of the sliding window. And this output over here is the ROI that we extract for the current sliding window. So as I advance execution of this script, notice how our sliding window is moving left to right. And then each step of the sliding window, we're extracting this ROI. So this ROI gets added to the ROIs list. And then the coordinates of this bounding box right here get added to our locations list. So let's slide our window from left to right and top to bottom. And as you can see, our ROI is getting generated. And as we'll see in the next step, right around here, you'll start to see the stingray is pretty visible. So if we extracted the ROI and then passed it into our model and asked it to make a prediction, it's likely that it's going to come back and say, with a reasonable probability, that this could be a stingray. And the same is true for all of the ROIs that contain a full or partial view of the stingray. Now, I want you to pay attention what happens when we get to the bottom of this sliding window for the image. What you're going to notice is that once we get to the end of it, the sliding window size is actually going to appear that it increases. Wait, why does that make sense though? I thought if we constructed an image pyramid and then we go up a layer, that the image size decreases, right? But the image size stayed the same, but the bounding box got larger. Does that make sense? Well, actually, yeah, it does, because our visualization here is saying, okay, our image is the same size. So if we want to make it feel like we're classifying a larger region, that means that our bounding box has to grow instead. So that's strictly for visualization purposes to show you that we are computing these coordinates with respect to the original input image. So yes, while we're doing this whole resizing step and constructing the image pyramid like we do here, and then perform the sliding window approach, these coordinates are still computed relative to the original input dimensions. And that is so critical when we go to apply non-maxima suppression. So we loop over each of these ROIs, which is what we're doing here, and then our lists will be updated. So that's essentially what we're done there. I'll show you the output of this script when we get a little farther on. So let's continue with our implementation. We'll take our ROIs list, convert it to a NumPy array, and then we're going to start a different timer. And we want to time how long it takes our model to make predictions on every single one of those regions of interest. That's going to take a little bit of time, especially since we're running on a CPU. If you had a GPU, obviously that would run much faster. So once our model has made predictions on each of these ROIs, we're going to decode them and get the top one prediction for each of our predictions right here. And then we're going to define this labels dictionary. And as you'll see here, our labels dictionary, the key is going to be the human readable class label. So that could be Stingray, it could be Beagle, it could be Labrador, whatever the human readable label is. And then the value is going to end up being a 2-tuple. It's going to be the bounding box location of where in the input image this classification took place. And the second value will be the probability of that classification. So let's unpack this a little bit more. We're going to enumerate each of our predictions. And then for each prediction, we're going to extract the ImageNet ID, the human readable class label, and the probability associated with that label from the current ROI. We'll then check to see if the predicted probability is greater than our minimum confidence. If it is, then we'll treat this as a positive classification, and we'll extract the bounding box coordinates associated with this location. Because remember back up to these lists here. The ROIs contain the region of interest for the current sliding window within the current image pyramid, and then this locations list contain the XY coordinates of where this ROI is. So that's what we're doing here. And we're going to update our labels dictionary by grabbing a list of data for the current label. If there is no existing data for the current label, we get an empty list back. And then we're going to take this list here and we're going to append the bounding box location and the probability. And we're going to put that back into our labels dictionary. So again, this is before we've applied non-maxima suppression. So let's loop over our labels dictionary, specifically the keys. And we're going to draw the bounding boxes for the current label, again, prior to applying non-maxima suppression. So for the current label, let's loop over the bounding box and the probability, grab the starting and ending bounding box coordinates, and then draw that on the output image. And we'll show the results before applying non-maxima suppression. So let's run this script. Actually, I'm going to kill off the visualize command line argument since we don't need it. We're going to generate our image pyramid. We're going to classify the regions of interest, which will take a few seconds since I'm running this on my CPU instead of a GPU. But when the results come back, you're going to see the raw bounding box coordinates. These are the bounding boxes that have passed this minimum probability test right here. Of course, there's only one stingray in this image though. So the question is, how are we going to collapse these bounding boxes into a single positive detection? The solution is to apply non-maxima suppression. So what we do is we extract the bounding box coordinates from our labels dictionary, and we extract the probabilities from our labels dictionary as well. That gets passed in the non-maxima suppression function, and that's what's going to collapse these weak overlapping bounding boxes. So our final output is to loop over the output of non-maxima suppression, draw the bounding boxes, and then draw the class label on that image as well. Final step is to show our output. So if you compare the output here, you'll see that we've collapsed the overlapping bounding boxes into the bounding box that has the highest probability that also factors in the overlap score of all of these bounding boxes. So in this example, it worked quite well. Let's see some instances of maybe when it doesn't work so well or our output isn't as desirable. Let's start with this lawnmower example here because this one is pretty interesting. And as you can see from the output, generating the image pyramid takes 0.13 seconds, which is a pretty considerable amount of time considering what this algorithm is doing. But what's more concerning is classifying all these ROIs took about 7 seconds. Now, if I had a GPU running on this machine, we could do that in a fraction of the time. But it just shows you how computationally hungry this algorithm can be. So here is the output for the lawnmower class. As you can see, we're getting tons of potential classifications. And if we apply non-maxima suppression, we're able to locate the lawnmower in the image. But there's a problem because we also get something called a half track as a second detection. And you're like, what is a half track? Well, half track is actually a military vehicle that has similar like a Jeep or a truck that has wheels, standard wheels, and an axle on the front. And then it has those tracks similar to like an excavator on the back. So it's generally used in situations where you need more mobility, you need more traction. And it's called half track because, well, the front is normal wheels and then the back is your track. So I guess it's kind of like a weird, like maybe mullet of a car, like party in the back, business in the front applied to a car. I'm not here to judge, but I think you get the general idea of what we're doing here. And one of the limitations is that there's clearly not a half track in this image. And I'll show you just Google it to show you. This is what a half track looks like. Clearly, there is not a half track in this image anywhere. It's a false positive detection. So what can we do in those situations? Well, what you want to do is update your minimum probability. So I'm going to update my min confidence from 90% to 95%, and let's see if we can get rid of that half track detection. So we've constructed our image pyramid windows. We've performed that operation. Now we're going to classify our ROIs. Sure enough, we get our lawnmower detection, and that's it. There's no half track output. Here, previously when we ran the script, we got a half track in the output. Now that has been removed. So let's now look at a final example of detecting a hummingbird. This is the example you saw earlier in this tutorial. And then we'll wrap up with a discussion on our results, including what worked, what didn't, and what we can do better. So looking at the output, here is before. This is all the positive classifications for hummingbird. We apply non-maxima suppression and we get the final output. So it worked in some situations, it didn't work in others. But I want to point out here, notice that I had to explicitly set the size of the sliding window for each of these examples. This was done empirically by trial and error, by examining the size of the ROI in a tool like Preview or Photoshop or Paint. So I had a general idea of what I thought the bounding box size should be. And notice that it's different for all three of these examples. The Stingray had one that was wider than it was tall. The Hummingbird example was a square of 250 pixels by 250 pixels. And the lawnmower one, also a square, but it was set at 200 pixels by 200 pixels. That's kind of the problem that you're going to run into using the sliding window and image pyramid approach. First, this procedure is slow. So constructing an image pyramid and running the sliding windows alone, that's going to take a minimum of a tenth of a second. And once you get through generating all those regions that could contain an object, then you got to classify them. On a CPU, that took about 4 to 9 seconds on a 3 gigahertz CPU. If you had a GPU, certainly you could get that number down to maybe a second or two, but still, you're not going to get real-time performance out of that. Also, the bounding box locations aren't necessarily going to be as accurate. That's due to the number of parameters you have to set here. You got to set the width of the input image or the height of the input image, the pyramid scale, your window step, your ROI size. Those parameters have to be tuned, and they have to be tuned on a per data set and potentially a per object instance. That's kind of a pain. It's a lot of manual tuning, and it's certainly prone to false positive detections or missed detections altogether. And then finally, this isn't an end-to-end trainable model, right? We just took a pre-trained image classifier and learned how to turn it into an object detector. We didn't actually train an object detection model. The reason why models like faster RCNN and SSD and YOLO, the reason those models are accurate is because they were end-to-end trained. They started with an input image and then the bounding box location and the label, and then computed a forward pass, computed the error, did back propagation, updated the weights of the network such that you create this end-to-end trainable model. Doing so is always going to yield higher accuracy. Our method here, there really isn't any true machine learning going on, right? Because this ResNet model, it's already been trained. We're just doing a little bit of a hack here to turn it into an object detector. But what you'll see as we go through this series of tutorials, as well as the next series in object detection on bounding box regression, we can improve our pipeline at each step of the way. Specifically, what we're going to dive into next is what happens if we can get rid of this image pyramid. Because if we can get rid of this image pyramid, we'll get a significant speed up in our pipeline. Get rid of this image pyramid, get rid of the sliding window approach. And if we do that, we'll gain a speed up right then and there. And that is what we'll be discussing next week. So stay tuned for that tutorial. I'll see you later.